Thank you very much. Can you guys all hear me? And
Yes.
okay, then. So today's webinar is going to be about building fiber networks in rural America. This should go about 45 minutes. And if you don't, some people have seen some webinars from me in the past, some have not. But one of the things I like to try and do is pack a pretty good amount of information in a relatively short period of time. So going to be moving through at a relatively quick clip. But would, as Sharon mentioned, encourage you to hold any questions, and we will have plenty of time for questions at the end. But we've we've seen a lot of new people developing fiber optic networks and building fiber optic networks, and really wanted to provide some guidelines for building these networks in rural America, where we have really we're at the leading edge of an unprecedented building cycle for fiber optic networks, across the U.S. And what's really neat about this is we're now seeing the promise of fiber to fiber to the home everywhere beginning to become the start of reality. So have a lot to go through, and we'll now begin. So just a little bit about OFS. We are, the way I normally like to describe us is we are the fiber optic arm of what was Bell Labs. And so Bell Labs was very famous for the development of the laser, the transistor, just a lot of very fundamental technologies, and fiber optics is one of those technologies. So we began working in fiber in I think it was either the 50s or the 60s. You look back in the patent record, which is just amazing to see just very fundamental patents, like taking this chemical, combining it with this chemical to put it in glass to change the refractive index. But anyway, the main point here is that we have been around fiber for decades and plan to be around fiber for decades more to come. Some innovations here in 1975, the first fiber optic ribbon that occurred, the LC connector, back in 1995. We won an Emmy Award in 2016, and have just been around fiber for a very long time. So a little bit of background on OFS, and from here we'll head into the agenda. So we'll talk a little bit about background and network basics. And I like sharing this because in many cases people understand that fiber is important, but they don't necessarily understand exactly why. And so we're going to give just a few slides on why fiber now is so important in in rural America. And if you can see what I have behind me, there's a little brick chimney. I'm in a farmhouse in eastern North Carolina that was built in the 1800s in a very rural area, and I'll show you a picture or two of that in a second. But we're going to spend some time on background and network basics and why it's so important in rural America. Fiber counts and types, how do we start to plan out some of these networks? And then we'll spend some time talking about rights of way and cable choices. So, this is primarily around the core network backbone and distribution system from a cable standpoint. And then we'll have another opportunity for other parts of the network where we go into a deep dive a little bit later. So just a little bit of background on kind of where we are, the digital divide in 2023. So digital connectivity is absolutely essential for a full life in 2023. The gentleman to the right side of the screen is my father. My father has Alzheimer's disease, and he lives in Atlanta. And I live, as I mentioned just a second ago, in rural North Carolina. And my lifeline to him every night is an Alexa Echo show, where I can see him in some detail. I can see whether or not his eyes are red. I can see if there are any new things around his skin. And but having that connectivity, and especially when that connectivity is not available, is just key. So connectivity to family, to friends, to services. And a large part of the U.S., especially in a lot of rural areas, still has very poor connectivity, especially upstream bandwidth. And the upstream side, a lot of our networks were built primarily for downstream bandwidth, and the upstream is increasingly important because of these kinds of issues. The times I actually have fiber to my home, and so I've got very good connectivity. He doesn't have fiber, and so when we have connectivity issues, it's on the upstream side where I can't see him. And it's extremely important to have both downstream and upstream connectivity. Luckily, help is on the way. The BEAD program is an unprecedented investment in telecommunications infrastructure for the U.S., and that's going to be a very important investment that will really will resonate for decades to come, if not much longer than decades to come. So the importance of bandwidth in rural areas. And so this was actually looking out my front door yesterday morning. And so if you look out in front, any of you who are soybean connoisseurs will see that those are some monster soybeans. But the increasingly with precision agriculture needs a lot of bandwidth and helping to map out fields and all of the kinds of things that are occurring in order to be able to just increase the yields that we have for agriculture. Certainly medical, if you're in rural areas in a lot of situations, and I'm one of those, my primary doctor is an hour away. And so anything that we can do to continue to improve medical connectivity to people in rural areas is extremely important. So I'm an engineer by profession, and without a good fiber optic connection, I would have a real tough time doing what I do from where I do it. So professionally, it's important. Educationally, we all hear about those stories where people hung out to do their homework in McDonald's parking lot or a rural area parking lot, and then personally, there's so many now applications. So in short, we need bandwidth in rural areas, as importantly or even more importantly than we see it in other areas, just because we need bandwidth to conduct life in 2023. So if you look at where we are, bandwidth demands continue to rise. And so this is 20 to 30% annual growth. What's interesting about this is that we find multiple organizations that do bandwidth projections, and they all end up at around the same numbers, although they may do their projections in different ways. So demand is also upstream and downstream, many different applications, and you can see those. I'm not going to go through them all, but there's really no end in sight. And another thing that's very important is that people and businesses increasingly factor bandwidth availability into location decisions. So if you're a bandwidth desert, that is for a lot of people, that is going to preclude them from wanting to locate either their business or their home in that area. So this graph over to the right side of the screen was something that the Fiber Broadband Association Technology Committee put together a few years ago. And you can see that we're in 2023, but we are continuing to anticipate, and we're seeing this happen. Just a lot of demand, coming from a lot of different areas, and this is not a magic demand. We've continued to see this trend for years and years, and so basically it has been roughly 20 to 30% annual bandwidth growth, and there's no reason to think that that's going to stop. So basically, whenever we get a pipe, people figure out how to find new ways to enhance our lives using that pipe. So some fiber facts: fiber has almost unlimited bandwidth, and so there is going to be a Fiber Broadband Association paper that's going to come out to really define this in a little bit more depth. But once you get fiber, especially in a rural area, you're kind of done. And that's why it's future-proof. There is roughly 400 or 600 plus terabits per second capacity in fiber. So I mean that is just a monster amount of bandwidth. And I think it was roughly around 60,000 times the bandwidth available in today's XGS-PON systems, which are 10 gigabits per second. So I'm tossing around a lot of numbers, but bottom line is there is a tremendous amount of bandwidth available, and we haven't even filled it up in the ocean. And so, certainly to rural areas, it's going to be a very, very long time before we actually fill up the bandwidth. So fiber is easily upgraded over time, either faster speeds per wavelength, more wavelengths, and you simply change out the devices on either end. I'm going to show you a map of some of those wavelengths as we continue on in this presentation. Fiber is a durable asset. So we've already made it roughly 35 years with fibers that were deployed, fiber cables that were deployed in the 1980s when it was brand new technology. So, we have those networks, a lot of them are still in existence, and the fiber that we deploy and the cable that we deploy today is significantly, well, the design is similar, the quality and our understanding is much, much better. So we anticipate multiple decades of lifetime. When people ask me how long will fiber last, my typical answer is basically the same amount. If you install it correctly, it's designed and manufactured and installed and operated correctly, the fiber in the ground or in the air is going to last basically as long as the desk I'm sitting at. So as long as I treat this desk well, I think it's going to be around for a very, very, very long time. And the exact same thing, as long as there's nothing around to kill fiber, then there's no reason for it to basically spontaneously stop operating. So again, there's some caveats there. You got to design it, manufacture, install it correctly, and operate it correctly. But that it's we've already seen it last 35 years, and we don't there's no reason for us to believe that it's not going to keep going for a very, very long time. So one other thing is that installation is often the largest fiber network cost, and one of the things about that is installation dollars can often circulate in a community. So if you're installing a network, the people who are installing that network may live in your community, so those installation dollars will continue to accrue back within the community, and that's a very important point. So some of the limitations around wireless and satellite. So I always didn't understand. I can never understand why why is not just 5G, is that not good enough, or 3G good enough, or 4G, or WiMAX, or a lot of these things. Why were they not good enough? And when you go to this, if you go out to NTIA, and you can, anybody can go out and find this. This is the United States Frequency Allocation Map, and I know you can't see this in detail, but this is basically an allocation of all of the electromagnetic spectrum that the FCC regulates. And what you see there is that there are a lot of colors and a lot of slices. And each one of those slices is something where a group that has a specific application has claimed electromagnetic spectrum. And so that means that the amount of spectrum for whatever communications we're using is very limited. So spectrum is allocated in slices in hundreds or thousands of megahertz. And by contrast, the fiber has roughly 50 terahertz of bandwidth, which depending on how you do the counting, 100,000 to 5 million times the available wireless spectrum. So that's why we're never going to get there with wireless. Wireless is a great technology and will continue to be a great technology, and has been from the beginning and will continue to be compatible or complementary with fiber. But wireless on its own has some limitations, and ultimately, either whether the wireless is in terrestrially wireless or even satellite, there are just fundamental spectrum limitations that means that these technologies just can't grow the same way that fiber can grow. And fortunately, I think we've now kind of figured that out as a country. And so that's why the upcoming investments in networks become so important, because literally once you do fiber, you're pretty well done. So looking at the actual network backbone and where you build. So if you're thinking about building a network and where you want to build it, and hang on a second, I'm going to do another. But so where we want to build networks, so networks are often classified as either backbone networks or access networks, and there are a lot of different terminologies around this. But basically, you have something kind of in the back of the network, and then you have something closer to the customer. And backbone networks are often designed in rings or in a mesh, and so that's where we're illustrating here with this little illustration. So you've got different districts, different counties, different whatever you want to call these, and these are all connected with these little dots. And the dots are connected either in rings or in a mesh. And, these rings or meshes can often be self-healing. So basically, if you've got a cut in one location for whatever reason, then the traffic can be rerouted around another area. And so that helps to provide just an additional level of resilience in networks. So backbone equipment can be housed in a variety of locations. So if you're in rural areas, what are the things that we typically have in rural areas? We may have substations that may have a trailer that's associated with, or a little building. So you can stick backbone equipment there. In community buildings, in schools, and firehouses, in some places we see standalone cabinets where these cabinets house electronics equipment. But the equipment can be stored in a variety of places. A lot of networks, as far as where these dots are, they are typically, can be typically less than around 24 miles between locations. And the reason for that is that the standard that we use in a lot of fiber to the home networks is called passive optical network, or PON. And the access equipment that's used there has a range of around 20 kilometers, or around 12 miles, 12, 13 miles. And so, that means if you draw a circle around, and you can see the circles here, then you would see the various service areas for different places. And so whenever you can, if you place equipment in the center of the service area, that can also help just from an efficiency standpoint, because if you place stuff in the middle, then you can reach out to each side and use lower fiber counts in order to get to pass the same number of customers. So continuing on with the fiber types, and again, this is meant primarily as a tutorial for people who don't have a lot of background in fiber networks. But there are two fundamental main types of fibers that are used in communication networks. One is called single mode, and the other is called multi-mode. And when I typically ask this question of audiences, what has more bandwidth, everybody says multi-mode, because it carries multiple modes of light. And it turns out that that's exactly opposite. It turns out that single mode fiber has the much more bandwidth, because it carries one mode of light. And with this one mode of light, that means that the pulses in that light, or the pulses, can go more closely together without spreading out. And so single mode fiber can go much longer distances, with much higher data rates. So if there's one thing to remember about this slide, is that we're typically using single mode fiber. We're not using multiple mode fiber. And this is actually a pretty important point, because I often get questions, and I'll remember from a network from a while back where we had an electrical co-op wanted to wire up their entire hundreds of miles with multi-mode, and we made the suggestion that may not be the best idea, and they came back and went back with single mode. So with fiber to the home, the vast majority of what we do is single mode, and we often use something that's either conventional single mode or the combination of single mode and bend insensitive. So one thing about fibers is if you bend them very tightly, then you potentially can have some light leak out. And so there are different grades of single mode fibers that we use to reduce the amount of light that ultimately can leak out of a fiber. And so this graph, and I'm not going to spend too much time on this, but as wavelengths increase and as the bends get tighter, then the attenuation, the loss, increases. And so we want to be very cognizant of this, because if we bend things too tightly, then it can cause loss in the network. Oh, and the alternative to that is to use bend insensitive fiber, and that can help you to do these bends with lower loss. So bending loss will become an even bigger challenge. A lot of the networks that we had been deploying were called GPON at 1490. And a lot of the networks that we're seeing now in rural areas are XGS-PON that are 10 gigabits per second upstream and downstream. And these operate at 1577 nanometers. And the bending loss between 1490 to 1577 increases 3x. And so this is something that we just need to be cognizant of. And so we can use it to help determine what fiber types go in different parts of the network. So, that was kind of the setup to this slide. And so in general, in the network core and drops, which is where we're talking about the majority of content today, we use a combination of 652D fiber, and this is an ITU standard, and 657A1 standard, fiber. And then there is also an A2 that's used for cabinets, boxes, and enclosures. And once we start getting into homes and into buildings, then there is a fiber called B3, and we use these all together. So they can be spliced, they can be connectorized, and they will operate together to really give you the optimum network. So, so I mentioned earlier about the optical spectrum, and that different wavelengths are used for different services. And this is a map of what has happened over time. And I'm not going to go through this in a lot of depth, but one of the things I want to highlight is that we continue to see lots of applications that use different wavelengths of fiber. So you can see the range, over the past, the past years, and now, kind of where we are today is we had been doing some GPON and EPON. We're now deploying 10 gig PON, which is either 10 gig GPON or XGS PON. And there's also a lot of discussion, and there are some commercial deployments of 25 gig PON, 50 gig PON. I've heard 100 gig PON. I've also heard 200 gig PON that are on the horizon. So, this is, again, one of the advantages of fiber is that the fiber has enough bandwidth to handle all of these applications simultaneously. And so what you can see here is you want to have a fiber that really can enable you to use the entire optical spectrum. And so, because it will ultimately be needed over the long period of time. And not all fibers are the same. So you can still buy some fiber. So this is an attenuation versus wavelength curve. And you can see that there's a big peak in this area that uses conventional single mode fiber. And this stuff is still available. And so this is why we want you to be a little bit cautious and make sure that you're buying fiber from a reputable source, because some of this stuff is still available. If you buy it, then you're going to get as you try and expand wavelengths to various different protocols, then you may end up with a unpleasant surprise with much higher attenuation than we would see otherwise. So there is also low water peak, and there's a lot of that has been deployed with OFS. Pretty much everything that we make is classified as zero water peak, and there are additional manufacturing steps that we do in order basically to make this attenuation curve as low across the optical spectrum as we can. And so also with a lot of the fibers that we make, we also include 657A1 capability. And the reason for this is that you can see the blue fiber there that's bent too tightly, and accidents occur in the network where people bend stuff too tightly. And if if you've got an outside plant fiber that has A1 and 652 together, then that can help to offset some of these mistakes that occur in the network, because we're seeing a lot of new people deploying fiber, and we want to try and make these networks really as fault tolerant as we can. So a lot of people are really surprised when they see this picture, and not all fibers are the same. So different manufacturers may use different raw materials for the glass. And so I want to highlight that fiber is typically a very small cost in the network. These are scanning electron microscope pictures of two different fibers. So the fiber on the left is a pristine fiber. OFS made this fiber. And the fiber on the right was from a different manufacturer, and so you can see that there are a lot of different bumps and humps and all kinds of stuff there. And just overall, I think I'm going to want the one that's a little bit cleaner in my network, because each one of these, especially if they occur closer to the surface of the fiber, could be a potential something that we need to be concerned about from a reliability standpoint. So you really want to have clean glass if you possibly can. So again, a question that I would get pretty constantly is, can you splice different fibers together? And to be very clear, single mode fibers from different manufacturers absolutely can be spliced together. So 652D and the various 657s can be spliced together. Fibers with different mode field diameters may show something called a gainer. These may increase loss a little bit, but they typically don't affect the network performance. So one thing I want to highlight, though, is we typically do not splice single mode to multi-mode fibers together. But single mode fibers of various types absolutely can get spliced together. And if you have someone who tells you the contrary, then they definitely have an agenda. So what to look for in fiber. The Fiber Broadband Association is in the process of putting together a document that is a trusted fiber document. And we know that, again, we've got a multi-billion-dollar build that's going to be occurring, and it's occurring with taxpayer money. And we think that taxpayer money should be used very, what's the word? Not cautiously, it should be used very well cautiously, but also in a way that we get good value for money. And so we've placed a lot of requirements and things in this document. I would you may want to look at that when it ultimately comes out. But ultimately, there are a few things to look for in fiber. You want to have low loss across the full spectrum to give you long-term viability for different wavelengths as the different services come on with different wavelengths. Good bending performance. There's something called PMD, which is polarization mode dispersion, that we haven't talked about. But this is actually an extremely important parameter, because there are fibers that are made today, and the baseline 652 standard, if you deliver just to that, you can actually get very high PMD, and that will potentially impede your networks as they start going in the 40, 50, 100 gig per second range. So PMD is very important for higher data rates. And certainly, we've talked about the glass material, synthetic silica, and then there's another parameter called dynamic fatigue for mechanical reliability. So there are a number of different things. Fibers are different, and it's good to do some homework to understand what you're buying, because different fibers can be different, the same way that different materials, all different types, can have some different criteria. So sizing the network. From a backbone standpoint, fibers are typically packaged in groups of 12. And so as a point that I made a little bit earlier, is fiber is typically very inexpensive, and extra fibers are typically very inexpensive relative to labor and electronics. And so if you're in a rural area, we see a lot of different network designs and network types, and those are fine. We see 144, 288 are popular for smaller networks. 6912 is the highest commercially available. We really don't expect to see a lot of that in rural America. But the one point about this slide and this one here is, as you're sizing your network, really it's good to think long term about all of the different applications. So, you're not going to get it right, but because, we're basically using a crystal ball to forecast, what kind of growth you're going to see long term. But if fiber is cheap, it's almost always a good idea to upsize a little bit, just to have the fibers available, because the fiber itself, relative to either the cost of the cable, the installation, is just so the incremental cost is so small. But looking at these, the core internal backbone, you may need 2 to 12. The fiber to the home backbone may need 2 to 12. Individual cameras and devices and switches, and if you're a power utility, reclosers, and all of these different devices that potentially could run over your network. You may need a fiber or two for each one of those. So the school system, the hospital, or doctor's network, they may want some fibers. If you've got other types of civic organizations, maybe you want to tie the firehouses together, and they have certain needs. So you've got think through the requirements for all of the aspects of your community. It also may make sense if you have a wireless provider that wants to come in and provide service in your network. If you've built your network and you've got enough fibers, you would potentially be able to to lease fibers to them so they would be able to operate. So leasing is something to kind of keep in mind. From a mobility standpoint, we often hear it. It really depends on the carrier and the number of carriers. But you may have up to 12 fibers per cell that could enable different competitors. Fiber to home distribution could be 36 with distributed splits. If you're using centralized splits, then you may need that may be higher. And I know I haven't defined what that means. So that actually would be part of a different discussion. And then you want to have some spares. So just keep in mind that there are just a lot of things that need to be thought of when you're actually planning a network. And so that's the main point about this slide is, again, think about, the long-term requirements for, for your network and for your community. So which right-of-way? So these are some just generic relative deployment costs. And in general, underground networks, digging is relatively expensive. But the costs for deployments can be dramatically different. Digging in an area where I live, not that expensive because we've got very, very, the dirt is very easy to dig through. And we have a lot of hurricanes in eastern North Carolina. So in some situations, maybe better choice to deploy underground. And other areas, it may make a lot more sense to deploy aerially because aerially can often be the faster deployment method and the least expensive. So there are a lot of trade-offs here, including permitting, costs, installation speeds, and then threats and resilience. And so, I'm not going to define all of those here because there are, just a lot of things to think through, but do want to highlight these are some things to think of. And so from here, going to go through and just give a little bit of background on what is actually happening inside of a fiber optic cable. And so the next couple of slides are around cable anatomy. So the cable anatomy starts out with an outer jacket, and this is almost always made of polyethylene. And polyethylene as a material has been around since the 1930s, and it has been studied. It has been studied a lot, and so we really understand that polyethylene, especially if it's carbon stabilized, which is what you get in reputable cables, then we know that is going to be around for a long time. I saw a study that was done for a different purpose that said that polyethylene that potentially would be in a landfill could be around for literally thousands of years. So I am not going to suggest that fiber optic cables and networks are going to be around for thousands of years, but we know that polyethylene as a material, is going to be around for a pretty long time. So as we go, into the cable, often, and there are different types, and I'm going to show a couple of different types of cables, but there's often a central member, and that's that little white piece. In some cases, it may be upjacketed with some polyethylene just to make the geometries work. And then around that, you may have some ripcords, you may have some strength members and water blocking materials. And then from there, you'll have the buffer tubes, and you'll have fibers inside of those buffer tubes. So that's a little bit around the anatomy of a cable. And this is a little bit more information about what and why. So they're most often either loose tube or central cable structures. And if you look over to the right, you can see that there is more fiber inside of this loose tube structure. And what that does, that's called excess fiber length. And that enables the fiber optic cable to expand and contract without putting a certain amount of strain or too much strain on the fibers. And so this is a very, the concept of excess fiber length is very important both in fiber optic cable design, manufacture, as well as installation, because from an installation standpoint, we give recommendations on the maximum amount of tension, and we'll talk about that a little bit more. But fibers are sometimes individual fibers, and they're packaged 12 apiece. Sometimes they're either in flat ribbons or rollable ribbons. So there are different types, and in all situations, fibers and buffer tubes are color-coded in order to be able to know which fiber is what. So there is a standard color code, and that is pretty common around the industry. So underground applications typically use either a direct buried armored cable or a duct cable that can go in. Aerial applications are either lashed to a messenger or are potentially self-supporting. And continuing on with some of the basics. So this is an end-on look at a loose tube cable. So as we showed a couple of slides ago, you've got a central member. And this, the central member may have some strength along with some, there may be additional elements, strength elements on the outside. And then you can see the buffer tubes with the fibers inside. And then there'll be some kind of a water blocking material. There may be some additional dielectric strength elements. And then finally, the outer jacket. And central tube cables are basically, they look a little bit different. So there's no central member here. The strength members on the outside, and what these can enable, they have different purposes. So these potentially, especially at higher fiber counts, can be smaller diameters and easier to do splicing for some of these. So there are different designs, and the different designs can be used in different applications. So one thing to touch on is that limiting fiber strain drives all mechanical reliability calculations, and we limit strain to less than 0.2%, and that means that the glass, the cracks, any flaws in the glass won't enlarge. And so this has been around for around 3 decades. And this is also one of the reasons that fiber has been well known for its outstanding reliability. And so if you're an end user, why this is important is if a cable manufacturer gives you either a maximum rated cable load or a maximum installation tension, that's likely, this is likely what they use as a criteria in order to come up with that number. And that's a number that you really should try and follow. So there are ADSS, all dielectric and self-supporting and lashed cables. And ADSS installation is typically a little bit faster. They may have lower tensions and less guying, no maintenance, bonding, or grounding. And if you're a power utility, you can place these cables up in the supply zone. But there can be some challenge with drop management. But there are some pros and cons for both ADSS and lashed. If you already have a strand in place, which is the fundamental component of lashed cables, then it's really a no-brainer to go ahead and use that strand. And also, if you're in high density areas, it may make sense for you to lash cables. But there's also a new alternative to lashing, and this is a little product called Sherpa CMS, or Cable Management System. And as you can tell, it's a little bit tough to see here. You can see the little red circles, but this is an ADSS cable with drop cable attached to it. And so these are ways to attach different cables together, similarly to what occurs with lashing, but these are EPDM rubber. And so this is just an interesting way of being able to couple cables together, to place them in aerial environments. And so in this situation, you had some drop cables that were separating on their own, and it was just a lot easier to place these little Sherpa devices. And what that helped to do was couple everything, made for a much cleaner installation. So we're starting to wind down towards the end of the presentation, but a little bit of guidance on how to choose the appropriate cable for an application. So you've got a number of different choices between loose tube, rollable ribbon, flat ribbon, and then on the cable structure, as we talked about a little bit earlier, there is a central tube cable and also a stranded cable. So how do we often choose those? And we find that as the fiber counts go up, we often see ribbons that are used, because with a ribbon, you can splice 12 fibers together at one time. But we're also seeing, and that's the reason for this arrow, we're seeing more choices in fiber optic cables, especially with rollable ribbons. We're seeing the threshold of where people are looking at ribbon to loose tube starting to drop, where it used to be maybe 288, 216, 144, and we're starting to see people entertain ribbon at much, much lower fiber counts. And the reason for this, with ribbons, and these are what ribbons look like, but basically there's a preparation advantage because these are 12 fibers together, and with these you can splice them 12 at a time, and so you can see that in this slide. So you're splicing 12 fibers versus one at a time. And that also means that there's much less downtime during an emergency restoration scenario. So, we're seeing people consider ribbons because, they can be spliced a lot faster during installation as well as, subsequent, restoration. So a type of rollable ribbon distribution. So distribution cables traditionally have been loose tube, but we're now seeing people consider rollable ribbons for the same application. So with a rollable ribbon, you basically have 12 fibers that are put together, and you can see that you can separate them. So once you can separate something out and pick out an individual fiber, there's really no need for a buffer tube anymore. And so that means that now you kind of have the best of both worlds. You can pull out individual fibers as you need them, and you can also splice them as ribbons. So we're seeing a lot of take-up of rollable ribbons as distribution cables because it basically gives you the best of both worlds. And so these can often give you also smaller diameters and weights than flat ribbon cables. So with drop cables, rural drops are often long. And actually, this is the, they were plowing in my drop, so this is the drop from my front yard. I've been lucky enough to have fiber now again from since 2012. But they were plowing, so there are different kinds of drops for aerial and underground deployments. Drops can be either pre-connectorized, on one end, both end, or they can be bare and you can splice them together. And, there really is not a lot of right or wrong here. It really comes out to, what's going to be most important for you and your organization. But, there are different types of drops. So, this is a mini LT. So this is a flat drop with a little buffer tube inside. And these can be done with or without toning wires. This is a different version that's a tight buffered cable, so it's very easy to connectorize. This is our round drop, and then this is an easy bend drop, which ultimately can be can be run both in the ground, and you can also run it up the side of the house. You can run it underneath siding. So it gives you a lot of flexibility on being able to take the fiber, all the way to and in your home. And that would be part of, the second presentation, on a lot of these topics. So I did want to highlight Mini TB because it's kind of an interesting product. It's a flat drop, and it actually has ultra bend and sensitive fiber inside. And what's interesting is if you strip off the black stuff here, you're actually left with an Invisalite cord. And if you can see the Invisalite cord, it's right next to the little adhesive tool. And so you could basically have the same cable that's used indoors and outdoors. You strip out the outside, and now you've got a 900 micron little cord that can run inside, either on the baseboards or potentially up on the crown molding as a really interesting alternative that doesn't require a box on the side of the house and can enable you to take a the cable all the way to the ONT in the middle of the house. So we have covered a lot of ground. From a summary standpoint, just to make some points. So fiber to the home is important for rural life in 2023 and beyond. Fiber is very inexpensive in the context of the overall build. So deliberately think about fiber counts. It's best to consider, high quality fiber and cable products for these networks. I would like to highlight that, I think I mentioned it earlier, but we are, OFS is headquartered in Atlanta. We've been U.S. based with U.S. manufacturing for decades. Many choices for rural cable builds for both the backbone and the drop. And then, as we're showing over here on the side, the best tool is always an open mind. This picture always kind of makes me chuckle a little bit because that's basically a mind that is being dropped into a head that is, keeping an open mind. But once I saw the toilet, I just cannot unsee a toilet in that picture. But I still think it's a very good picture because, we're highlighting we're highlighting that you need an open mind, and there are a lot of different choices to make with with networks. So from here, that is the end of the presentation. Certainly feel my contact information is there. Certainly feel free to contact me. And from here, I haven't looked. We'll see if there are any questions, and then we will take questions. So let me drop down and see if. Okay, so I am seeing some questions. Oh gosh, I'm seeing a lot of questions. So I'll start with these. So ZBLAN and multi-core fibers. So ZBLAN, I actually don't know that acronym, and so multi-core I certainly understand. The potential of these fiber types compared to what is typically in use currently. So the question is for, since I don't know what the acronym ZBLAN is, I assume it's zero bin something, but I'm not sure. And local area network, but multi-core is actually a fiber with multiple cores in them. And so multi-core is a fiber that has been a concept now for 10, 15, maybe 15 years. And we are beginning to see where that could have some applicability, but where we see multi-core, and this is one fiber with multiple cores inside. So where we think we will see that most to start with is either in data center areas where you are limited in space and you need to provide tremendous amounts of bandwidth. There is also interest in multi-core in submarine applications where, again, you want to keep everything very, very small, and you want to be able to transmit as much information as you possibly can. So for fiber to the home, I don't see these types being used for fiber to the home now or anytime in the existing future, given that what we have in just a standard single mode fiber, again, is roughly 60,000 times, the capacity is roughly 60,000 times what we're doing with the next generation of deployment. So I don't see them being used in the access portion of the network anytime soon. So let's see, what brands, models of material are current, models of equipment are current. So I'm not going to make any recommendations on brands and models of equipment. I would like to highlight, so recommended now for home connection. There's something I would like to highlight is some of the bend and ultra bend and sensitive fibers can be used to run fiber inside the home. And I would keep my eyes peeled on that space because, where fiber has been used primarily to the home, we're now seeing a lot of, or some business cases that will enable fiber to go, into the room. So basically fiber to the room. And so I would say keep your eyes open on that space because that, is a potential application that you will probably start to see some more over the next 6 months to a year of fiber to the room because it is now becoming very viable in comparison to other alternatives. So Dan Sullivan, I see you, and thank you very much for the question. So have you done any research regarding rodent mitigation? Rural means a lot of aerial and squirrels. So the answer is I have been, that is a really interesting question, and I have been involved with squirrel stuff now for a very long time. So I made a first trip back in the 1990s to the National Wildlife Research Center in Fort Collins, Colorado. And at that point, they wanted to charge the company I was with $100,000 to first determine whether or not squirrels could taste anything. And so, at that time, we were looking at the use of either bittermints or capsaicin, types of peppers to be placed into cables as deterrents. From then, I have continued to see a lot of different manufacturers offer products that they would consider to be either squirrel proof or squirrel resistant. We also see people recommending the use of armor in aerial applications for squirrel resistance. And frankly, I'm skeptical for all of them for a wide variety of reasons. So first of all, from a capsaicin standpoint, which is again hot pepper, there was a really good paper by Corning. And so, I give a shout out to the people who did that study. And this was probably, 2, 3, 4 years ago, about just looking at capsaicin in these cables, because it was being offered as a squirrel resistant medium, and given, and they highlighted that it really would not be very effective for any significant period of time. So and then from an armor standpoint, as soon as that squirrel has penetrated the outer jacket of the cable, then ultimately that cable is going to need to be replaced at some point in its lifetime. So the armor, armoring is typically not, the metal armor is typically not hermetically sealed in a cable. So ultimately, once that jacket goes in, there is a very high likelihood that water is going to be able to permeate. Once you have water that can permeate, water can freeze, especially up in Saskatchewan. And, when that starts to occur, then ultimately, those freeze-thaw cycles are going to cause problems long-term. So, so I'm taking you the long way. I wanted to give at least a little bit of background. And so the shorter answer is, what we have seen from a squirrel mitigation that, can give some, that, really does give some relief is number one. And this is kind of a no-brainer, is tree trimming. So, having an appropriate tree trimming program is going to be very important. The second thing is, I have heard from various customers that pole wraps. So, pole wraps that make it very, very tough for the squirrel to actually get on to the cable surface to start with. So you put the pole wraps below, and the squirrel can not actually go up and jump onto the onto the cable. The combination of those are both helpful. I've seen other manufacturers that have mechanical squirrel resistance items. I actually have some thoughts on my own for some squirrel resistance items, but these would be mechanical things that are mechanically you're basically stopping the squirrel from actually doing its chewing to start with. So I took you a long way around that, but I hope some of that helps. Newer connector innovations that are coming out. So there are newer connectors that that are around. A lot of those are focused on primarily on density and just trying to make the footprints a little bit smaller. For fiber to the home, we see either the tried and true LC or the SCs as being the the most common, and the newer ones right now, the types, I've seen them, and their names are just poof, have escaped my head. So sorry, I can't give you the exact information, but there are some that are looked at, but they are looked at primarily from a density standpoint. If you're in data centers and those kinds of things, and you really want to cram space. So why are fiber specs for 1650 not published, since this is required for OTDR? I know, and I know that they're required at 1625, or we see a lot of groups at 1625. So 1625 is, and I have to go back at all my wavelength maps, but I think those are primarily where the majority of operational wavelengths end. There may be some applications that end at 1650, but they're not at the top of my head. But certainly OTDRs can be used as a monitoring wavelength, but they may not necessarily be used as an operational wavelength. So Mike, it's a great question. That is the best I can do to answer that one, and I'm not sure if I've answered that completely perfectly, but I hope that helps. So any additional questions? I really appreciate the questions coming in and people hanging out for the end of the end of the presentation.
Thanks so much, Mark. The squirrel story was so good.
I wish I had a magic wand. and to solve that one. And believe me, there's been a lot of brain power that has been thrown at that, and the squirrels are just smart.